So hello again everyone. So I hope you guys are all having a good day. So I was just done with the engineering economy lesson. So now we will move on to the applications of differential equation. So we have the first application, which is the growth and decay problem. Okay, so it is also called sometimes the population problem. So I will be deriving the formula first for this one. It is quite short and quite easy to remember, but I am really into principle first before we get to the sample problems. Of course, I'll be solving some sample problems later on. So for the growth and decay problem, it is noted that the rate of change of the present amount x. So we can have here, remember that we will be using x as the present amount, okay, for the derivation only. So is directly proportional to the present amount, okay. So we can say that using the lesson in algebra, we can say that the rate of change of the present amount, rate of change with respect to what? The rate of change. Of course, that will be with respect to time because the x or the present amount changes over time. Therefore, we can simply say that this is dx over with respect to time. So the change of x with respect to time, it is now directly proportional to the present amount, which is also x, right? So directly proportional to the present amount, so x. So if we do this, we can also represent this as, oops, okay, dx all over dt. If I will make this equal, you must have here a proportionality constant. The usual letter or the symbol that we use for that is k. So we will have here a k times x. Okay, and then now we have to perform integral. But with that, if we will perform integral, we have to put all the x and dx and all the dt into each other sides, or we have to separate them. So this x must be with the dx. Therefore, I have to bring down, this x down, and then this dt will have to go with the k. Therefore, bringing that x down, you'll have here dx. Okay, so dx over x, and it must be equal to k dt. So now we can perform the integral. So integral and then integral. And then we have the present amount of x. So as you can see, this is a growth decay problem or the population problem. So for example, sample problems of this one, let's say a bacteria. So a bacteria grows over time, right? So it grows in a very fast rate. So let's say that the bacteria count now is, let's say, 100, only 100 bacteria. Then the question is, when will it be uh, 1,000 bacteria. Okay, the count of. So that is the a sample problem that can be solved with this formula. So therefore, the initial amount of the bacteria will be 100 and the final amount of the bacteria is 1,000. Therefore, this dx over x and k dt, it must have a um, limits. Okay, so the limits for this will be your PO or the initial amount. So we'll be using PO is the original amount or the initial amount, and then of course the limit, it must be from the initial amount to the final amount, which is we'll be using as a symbol of P. And of course this is from present time, which is 0. Okay, and then from any time, which is T. Okay, now performing the integral of dx over x is that is just ln x. Of course, we have a limit of PO to P. And then the integral of k dt is just kt. This is from 0 to t. t. And then continuing this one, we have to apply now the limits. So applying down the limits, you'll have here ln, of course, upper limit minus lower limit, upper minus lower, that is ln p. Okay, this one first, the upper limit, and then minus the lower limit, ln po, and then equal to k. The upper limit is t, and then minus the lower limit, which is k times 0. Of course, this one will just be 0 because any number multiplied by 0 is 0. Now, if you will apply the laws or the properties of logarithm, you can represent this ln p minus ln po with ln p over po, right? If it is subtraction or minus, it will be like this or divided to each other. And then if that is plus, it will be multiplied to each other. So this is equal to kt. Now, if I want to eliminate ln, I have to get the e of both sides. So getting the e of both sides, you can see that you will have here e ln times p over po, and then this will be equal to e raised to kt. Now, every time that e and ln are beside each other, they cancel out each other. Okay, they always cancel out. So canceling this out, okay, canceling e and ln, you will left here with p over po equal to e raised to kt. And then finally, cross multiplying po to e raised to kt, the final now formula will be p will be equal to po times e raised to kt. So this will be the formula for the growth and decay problem. Okay, so with this one, okay, so let me put the symbol. So P is your uh, final amount. Final amount. PO will be your original, original or initial amount. And then K is your proportionality constant. Proportionality constant. And then of course T will be your time. So that will be the derivation and for the formula for the growth and decay problem and population or population problem. And this will be your the symbol. Your P will be your P here is your final amount, PO is your initial amount, E is your proportionality constant, and T is your time. So with that, let's proceed to the sample problems. Okay, so let's go to our first problem. So we have the population of a country doubles in 50 years. So how many years will it be 3 times as much? Okay, so let's put the givens first again. So we have a given. So the population of a country doubles in 50 years, right? Therefore, we can say that T is equal to 50 years. Okay, and then what will be your initial amount and your final amount? So your P and your PO. So as you can see, if the population of the country doubles in 50 years, therefore the initial amount or the final amount will be twice as the initial amount after 50 years, right? So that means if this year is 100,000, after 50 years it will be 200,000. So we can simply say that the uh, final amount or final population is twice the initial population after 50 years. Therefore, if you want to make it into a equation, they can have simply that is P must be equal to 2PO. Okay? So you have to multiply the initial amount into 2 to get the final amount. So this is your first condition. So this one is your first condition. Now, if you want, now we have the second condition. So how many years? Okay, so how many years? That is, we are required to find how many years. So that we are asked to find t. So this must be in years at 3 times as much. So 3 times as much. 3 times as much. Okay. So this will be your second condition. Second condition. Okay, so we already have the formula, right? So the formula for that is just simply, I just put it here. P must be equal to um, PO e raised to KT, right? But usually, okay, most of the time, the first step that you want to do here is to find the value of K, which is a proportionality constant. Okay, so to find K, we have the only purpose of the first condition. I remember that the purpose of the first condition, just make it smaller. Remember that okay. Note that purpose of first condition is to find the value of K or the proportionality constant. Okay, so this is usually the purpose of the first condition, just to find the proportionality constant. Okay, so we have to use the first condition to get the proportionality constant. So using the formula with this one, so P must be black. So P, so using the first condition, you'll have here P equal to PO, right? PO e raised to KT. Now substituting the values here, we have T must be equal to 50, and then P, we have to replace P by 2PO. Okay, so replacing P with 2PO, you have 2PO must be equal to PO, or the original amount or initial amount. This is E raised to K, and then your T must be equal to 50. As you can see, there's a PO both sides, so you can cancel that out. So cancel this one and then cancel this one. You can have 2 must be equal to E raised to K times 50. And then again, the purpose of this one, if we have to find the value of K. So we have to find the value of K here. So finding the value of K here, taking the ln of both sides. Okay, so take the ln of both sides. Take the ln of both sides. Okay, you'll have here ln2 must be equal to ln e k times 50. As I said earlier, with the properties of logarithm, every time that you see ln and e beside each other, you can cancel them. They cancel out each other also. So we can cancel this out. Therefore, you will be left with um, ln2 will be equal to 50k. And then finding the value of k, you'll have here k is just equal to ln 2 all over 50. So this will be the value of k. Now using the second, so we already find the value of k. Now let's use using the second condition. Okay, using the second condition now. Um, Now we have to find t. So again, the formula is just the same. We have p equal to po e raised to kt, right? And then, as you can see, this is three times as much. Okay, three times as much. So if your initial population is 100,000, so after t years, whatever that year is, the value will be, now the population now will be 300,000. So we are asked to find when will that happen. Okay, so we are asked to find t. So we can say that the initial amount, we can say here that the final amount or final population must be three times the initial population. Now, if you will make that a equation, you'll have your final population, which is p, or the final amount, must be equal to 3 times the initial amount, which is p. Oh, okay. Now we can substitute this. Substitute this value to the formula. Here, you'll have 3 po must be equal to po e raised to kt. We already have a value for k, which is ln2 over 50. So ln2 over 50 times t. Okay, as you can see, there is again po on both sides, therefore I can cancel this out. Okay, so canceling those out, you will be left with 3 equal to e raised to ln2 over 50 times t. That is a power, right? That's an exponent. And then taking the ln of both sides to find the value for t, you'll have here ln3, and then again ln e times this one. Again, ln e will be cancelled out, so you will be left here with ln2 over 50 t. Therefore, the value for t will just be simply cross multiply your 50 here to ln3, and then ln2 will go down. So you'll have here 50 times ln3 over ln2. So let's try this one using the calculator. I hope you are doing this at the same time with me. So this is ln3 over ln2 times 50. So the answer is 79.24. So that is 79.2481 years. Okay. Therefore, that means after 79.2481 years, the population will triple. Triple, or will be three times as much as the initial amount. So I hope this is a clear one. If you have any question, feel free to comment down below. And let's proceed to our next problem. Okay, so for our next problem, we have in 100 years, 100 milligram of radium decomposes to 96 milligram. So how many mg will be left after 300 years? So as you can see, there's a 100 milligram of radium, and then it decomposes to 96 milligram after 100 years. So we are asked to find how many milligram will be left after 300 years. Okay, so let's put all the givens first again. So we have a given. So we have 100 years. So we have t must be equal to 100 years, and then your initial amount from 100, it became 96. So your initial amount now will be 100 mg. So your PO must be equal to 100 mg, and your final amount will be your 96. So that's P. This is 96 mg. Okay. Now we are required to find what? How many mg will be left? Okay, will be left. Therefore, we are looking for the final amount. Okay, so P. So this must be in mg at t equal to 300 years. So again, we can say that this one is your first condition. This is your first condition, and then of course the next one will be your second condition. This is your second condition. Okay, so let's do the formula. So for the formula, we have, let's see, using the first condition first. Using the Again, the sole purpose or the purpose of the first condition is to find the value of k. I hope you remember that. So again, the formula for that is p equal to po e raised to kt. Okay, so applying the first condition, you'll have your p now is 96, right? 96 equal to your po is 100, e raised to k times t is 100. Okay, so now we can find the value of k. So finding the value of k, you'll have 96. This 100 must go down, right? So this is 96 over 100 equal to e raised to k times 100. So again, taking the ln of both sides, you'll have here ln 96 over 100, and then this is equal to, again, ln e. You'll have your ln e. Every time that e and ln are beside each other, they will cancel out. They cancel out each other. So you'll have here just k times 100. And then finding the value of k, you'll have here k is just equal to ln 96 over 100 all over 100. So this will be the value for k. Now, using now the second condition, using the second condition, the formula is still the same, of course. We have po e raised to kt. But for the second condition, we'll be using this condition. T must be equal to 100 years. So P is the one that we are looking for or the required to find. And then what is PO? Of course, PO is still this one. You still start with 100 mg. Okay, so your PO is still 100. Okay, and then e raised to value of k is this one. So this will become ln times 96 over 100 over 100 again. That is your k times t, and your t is 300 years. This one times 300. Remember that this is our all in exponent of e. Now, if you will solve that, I think can try that out using our calcu. That's e raised to ln 96 over 100 all over 100 times 300. Nope. Okay, so the answer will be 88 88.4736 milligrams. So this will be your answer. So that means after 100 years, so you can see from 100 years, it will become 96 milligram, right? But after 300 years, it will now become 88.4736. Because remember for this lesson that the growth of bacteria or the whatever is usually exponential. Okay. So maybe some of you are wondering, if you look at the first condition, the initial amount is 100 milligrams, right? And then it became 96 milligrams in 100 years. That means um, the value decreases by 4 milligrams in 100 years. Now, if you find, and now what is asked is to find how many milligrams will be left in 300 years. Now, if 100 years is equal to 4 milligrams, then you will say that 300 years must be 12 milligrams. Therefore, 100 minus 12, and then the answer is 88. That is already wrong. Okay, that is not simply the case because the decomposing of the radium is not that simple because the radium decomposes at a exponential rate. That's why it decomposes at exponential rate and the population increases at exponential growth. That is simply the answer. So you cannot simply do that. Okay. So I think that's it for this video. And again, if you haven't already, of course, don't forget to subscribe to my YouTube channel and hit the bell notification so you'll be notified as soon as I upload a new one, especially during these online classes. And I already have a new subject to discuss this because I am already done with the engineering economy. So I'll be uploading more videos about the application of DE. So stay tuned, and I want to thank you all guys for watching, and I'll see you on the next one. Bye bye.